So, we were talking about chromatography the previous class before. So, here chromatography has the main part of the chromatography system is the column, which is also called as the stationary phase, and there is a mobile phase. So, the purpose of the mobile phase here is and then you introduce the sample, which is a mixture, is usually a pulse or finite volume just before the column, and then you have the separated components coming out of the column, which are then detected. So, there are very specific components of this. So, the main purpose of the column is the separation. So, the separation occurs mainly because of the affinity, different affinities of it takes advantage of different based on different affinities of the analyte between the stationary phase and mobile phase. So, in other words, we are talking about some partition constant between the stationary phase and the mobile phase. Okay. So, the extent of the separation depends on the type of this thing. So, for just give you an example, the higher the value of this thing for high K, this is high retention in the column, low KSM, which means low retention in the column, which means if you adjust, if you are able to somehow manipulate the retention time in the column, you are possibly able to separate some of the components that are in the mixture. So, this is the way which we manipulate the retention time. So, if you manipulate, so there are two factors that that control separation. One is this retention, one is this partitioning constant. So, we summarize factors affecting separation. One is the partition constant, KASM, whatever we are talking about. Okay. How do we adjust, how do we manipulate the partition constant to increase it or decrease it? One way is the temperature. We adjust the temperature, one factor. So, typically high temperature leads to low KSM, which means low retention. So, higher the compound comes out quickly. This is one. Second is you change the stationary phase. Yeah. This is far more difficult to do because stationary phase is sometimes very expensive. So, we do not want to, though it is possible theoretically, difficult to have a large number of stationary phases for a given set of analysis. So, chromatography columns are typically fairly expensive now, commercially available columns. Also, one of the things we would like to do when we are talking about affecting separation is we want to do this dynamically. We want the opportunity to do this dynamically. What we mean by dynamically is in a given sample. Okay. So, in a given sample means suppose you have 100 analytes in a mixture. So, 100 analytes, 10 belong to one group, 10 belong to group A, 10 belong to group B, and so on. There are different types of compounds in this, and you do not want to use the same set of conditions for all of them. So, you like one of them at one set of conditions, partition constant, other one at another partition constant, so on. So, you would like to operate this at differing conditions of partitioning within a run, single run. So, normally when you inject a sample, it starts the beginning of what is called as a sample run. The sample is running through the column, it is a run. Okay. So, within that time your goal is to do it all in one analysis, one shot. If you cannot, then you have to run it again with a different set of conditions, that is but the goal typically is to optimize the analysis, because analysis takes time, analysis costs money, and therefore we are trying to minimize all of that in a commercial scale. So, stationary phase, usually stationary phase changing is not done, but it is done for large groups of analytes. For example, if you know that your analysis, you need to do analysis for one set of compounds, alkanes or PAHs or PCBs or pesticides or something, you already know that you are only interested in this, and the column that you have is not suitable, it will give you a very unreasonable separation and not good. Then you go and select a stationary phase that is suitable for this. Otherwise, we will stick to the most generic columns. And last class we talked a little bit about this. The most generic column are some samples columns that are that would do a very wide range of separations. Okay. So, the third thing that you can do is change mobile phase. This is a possibility. These three things are the only things that are there in the system to change partition constant. Yeah. Because now you are changing, when you are changing stationary phase, you are changing this, which means you are introducing a compound that has a greater affinity to an analyte or lesser affinity to an analyte. Similarly, you can also change the mobile phase, you can introduce a compound that is greater affinity or lesser affinity. For example, mobile phase could be water, or mobile phase could be something like acetonitrile. So, if you look at water and acetonitrile, water is more polar than acetonitrile, obviously. Yeah. So, you are increasing the decreasing the polarity in this case by changing it from water to acetonitrile by a little bit. So, acetonitrile and water are miscible, which means that you can gradually change the polarity by adjusting the ratios of water and acetonitrile. So, you can make a mixture of these two, 1:10 or 2:8 and so on. So, you can gradually change this thing. So, last class we discussed that you can change the temperature gradually, you can also change the composition gradually. Okay. So, these are the three things that you can do to change the partition constant. So, dynamically you can do this dynamically, you can do this also dynamically. This you have to do this before the analysis is done. Stationary phase, you completely want to get one kind of separation, you do that. The second factor that you can play around is the velocity. So, this velocity and flow rate are components that will influence, because you realize that both these components, both partition constant and velocity flow rate, influence adsorption, desorption cycles, rates. Chromatography is a series of adsorption and desorption cycles that we are looking at and as the overall separation in a given system is influenced by these parameters. So, you can play around with these parameters and say, so there is something called as the rate of adsorption desorption depends on what is called as the mass transfer coefficient. We will talk about it later. For now, generally the efficiency at the rate at which mass transfer occurs is faster when you have large amount of flow tablet. But it is also there is a compensation, because if you have high flow rates, the compound does not have enough opportunity to do mass transfer. It is out of the system before it's completed. It may not even come to equilibrium, or it may not finish what it wants. So what is the objective of the mass transfer, and therefore there is a payoff. The effect is not just straightforward. Simply, it does not mean that the separation is greater or lesser, but overall effect of velocity is there. But you can guess, if I increase the velocity, the compound is going to come out faster, the retention is going to be lower. Yeah. But separation is a different aspect, because separation also involves partition constant. So, it is a complicated equation to solve. So, it is what in packed bed adsorption, it is an unsteady state problem. It changes at the length of the column and as it is going through. So, we will not discuss that too much here, but from a very rule of thumb heuristic point of view, you need to know, if you are looking at separation, you would like more time to be spent in the column. That is the only way you are going to separate. You are going to stretch the separation. That is the only way. You hurry compounds to come out, they will not separate. They are likely to get clubbed together. But on the other hand, if you have 100 samples, let us say I have collected 100 samples and I want to analyze in a system, I cannot wait for a long time for analysis to finish. So, I am also trying to optimize my analysis method, so that I can finish up as quickly as possible. I can analyze all the 100 compounds in each sample and do 100 samples in a reasonable amount of time, what we call as turnaround time for the analysis. So, chromatography, people have worked a lot on it. If you look at the literature on chromatography, even if you look at if you take a catalog of any chromatography system, they are all companies that are designing chromatography systems are all working at currently. This is all very old. Chromatography is fairly old, but now current systems they'll say ultra rapid chromatography separation, which means they don't want to spend even this much time. They want to do it very quickly in a matter of something which used to take 25 minutes, they want to do it in 2 minutes, which means it will increase the number of sample throughput and all that. So, the sample becomes more efficient in analysis. So, that is the engineering part of it, which relies on some of these basic factors. Okay. So, last class we also discussed, we were discussing mainly the gas chromatography. So, in this context, gas chromatography, the analysis, the mobile phase is a gas. Is a gas. Typically, it is nitrogen, helium or argon, which are inert gases. But sometimes we also use other gases. We can also use hydrogen and something else. Depends on what your analysis is specifically. There is a column. You can use packed columns or capillary columns. We discussed this. Packed columns, very simply, the packed columns are columns which contain a packing. Their length is anywhere maybe 1 to 2 meters or even slightly longer. One big disadvantage in packed column is that your pressure drop is high. The efficiency of separation is high if you give it a large opportunity for the compound to separate. If you give the length of the column long enough that it will separate, and it will separate nicely. So, if columns are long, it provides a large opportunity, because it is adsorption desorption. Even if there is a very small difference in adsorption desorption, if you provide a large distance for the adsorption desorption to occur, the separation will be effective. So, therefore, it is good to have efficiency of separation is high with long columns. Unfortunately, if you have long columns in a packed column, pressure drop is very high. You can't have columns beyond a certain length. So, separation is kind of restricted. So, to remove that, we people developed what is called as a capillary column. Capillary column is where it's a column that is made of glass, which has a coating of some plastic. So, this outer core is glass silica, and there is a coating of the stationary material. The S, what we are talking about, the stationary phase is coated in here. So, it is a small column. So, its dimensions ID is anywhere from 0.25 mm to 0.53 mm. And the film, the stationary phase is of the order of a few tens of microns, 10 microns, 1 to 10 microns, very small. So, this length of these columns can go up to 30 to 60 meters or even longer. So, very thin, they can be wound. Yes.
Is the packing like the distillation column packing is some other kind of?
It's just packing. It's just a pack bed, a simple pack bed. The pack column. In the pack column, the stationary phase is usually beads, spherical beads or some beads, which are commercially made. With some, they may have some coating or they may have the entire bulk, because everything is happening on the surface. Is inside, the more the larger the particles you have, the greater mass transfer issues and all that. So, the particle size is also small, but the smaller the particle size, bigger is pressure drop and all that. So, there is a design aspect there, but capillary columns remove that restriction. But because capillary columns are very small, you do not use very high flow rates through capillary column. Velocity, you can't run it at very high velocities, the pressure drop will again increase, and you can't have it at high pressures also, because there is a glass column. Even though it is flexible, it is like an optical fiber, it is flexible. So, normally the capillary columns are wound like this. They are wound like this. One end, this is the entrance to the column, and this is the exit of the column. So, this 60 meters of column looks like this, it is tied up. Okay. So, right here there is an entrance zone here. So, your mobile phase is, which is, we also call it as in the gas chromatography we call this as a carrier gas. In gas chromatography, the mobile phase is called as the carrier gas. This carrier gas is stored in some cylinder or some such this things commercially available, and it is sent in at some flow rate or some pressure. Here I have to introduce my sample. This is where we stopped. We discussed this and we stopped it here, and right here we have a detector at the exit of this column. This is the schematic of this. Okay. So, a variety of so this is the general arrangement of the capillary columns. So, this section, this column is kept in an oven. So, in the case of gas chromatography, you cannot change the mobile phase too much. Mobile phase is a cylinder, you can't adjust composition of cylinders. So, you cannot do much with the mobile phase. If you want to influence separation, you can only adjust velocity by changing the pressure, there is the pressure of the inlet gas, or you can change the temperature. So, in GC, generally temperature is the most flexible factor or parameter that influences separation. So, you can run the entire analysis as temperature profiles. You can start at one temperature, go up, and you can keep doing whatever you want. You can keep going up and down. You can program the temperature in a particular analysis. So, now we quickly look at some of the detectors that we have for GC. Yeah. So, there are a few commonly used detectors. The first one is called as an FID, it is called as a flame ionization detector. It is mainly used for hydrocarbon analysis. We will not go very much into details of this, as the name suggests. What the flame ionization detector does in general is that they are all based on some kind of electrical measurement. The signals are all electrical measurements. So, in this case there are two contact points in between. This whatever sample is coming out will burn, sample burns, sample combusts. Okay. So, if you are looking at the very simply speaking, there is this is from the GC column, this is the GC column from the exit, gas is coming out and it goes in. There is a region, there is an element here, there is an element here, these are two contact points. So, the gas is going through this, right here it burns, in this region there is a flame, there is a flame here all the time, and if there is a hydrocarbon in the in your gas, it burns. And to burn you need to provide a fuel. There is hydrogen and air, a mixture is added at this point here. There is a flame and this flame is burning constantly, and in this flame whatever is coming in also burns. When it burns, it changes the resistivity between these two points, electrical points. So, it is measured as a signal that comes up, and this, if you have more hydrocarbons, more burning happens, and therefore the signal goes up and comes down. So, so in the output, when you are measuring signal, you have injected the sample at the beginning of the column, and the sample is going at some flow rate, it is going out, and the moment it comes out, it takes some time for it to come out, and the detector detects it. Okay. When it detects it, there is this continuously is happening, there is detecting a real time change in the intensity of this flame. So, you may have what is called as a baseline, this may be the baseline, only the carrier gas is going in. When you have a sample, the signal may go up like this and it may come down, this is a signal. So, this is a signal for one particular compound. So, you may have multiple compounds, each one coming after the other, you may have multiple things coming one after the other. So, hope is, because it's chromatography, your hope is that this peak that you are looking at is only one compound, it is not a mixture of compounds. So, the resolution, the separation, you need to be sure that this is separated. That is a big challenge in analysis of mixtures. Okay. So, so anyway, so this is the way the detector represents the signal. So, this is called as, this is a response. So, in the case of FID will give you some response, its raw data is in terms of millivolts or some such unit. Okay. And you have to convert it to your units that you are comfortable with. For you, whatever is comfortable is concentration or area or some such thing. Okay. So, we do not do anything here, this is a response, and this data as it appears is called as a chromatogram. This is our raw data. The chromatogram is the record of the signal as a function of time as the compounds come out of a detector. Okay. So, now in this the FID does not care what the compound is, as long as there is something burning. Okay. This is what we call as a non-selective detector. The only selection it does is if it is a hydrocarbon or not. So, the hydrocarbon, what is the definition of hydrocarbon? You need to have C and H in your compound, that is all. If you only have C, nothing will happen, it will not detect anything. H has to be there for it to detect it. Okay. But it is non-selective, which means anything that has C and H, it will detect. It does not know whether it is benzene, acetone, alkane, ethane, hexane, nothing. It will just detect as it is. Okay. So, what is it that if you are doing an analysis that you need to know? So, we have two things that we do in chromatographic analysis. One is called as qualitative analysis. Qualitative analysis answers the question, what what is the analyte? And quantitative, you are asking the question, how much? What is analyte means, what is the identity of analyte? If I have an unknown sample, I inject it, I need to know what is what. And why do we need to know what is what? What is analyte? We need to know this question, answer to this question. We need to know the answer to this question in order to answer this question. Why is that? What do we need to know before we do quantification? Quantification means the answer to this question is some number, some concentration. I have 10 milligrams per liter or something. So, this is a number that I am going to report to somebody as some concentration. To get this, what do I need?
What you are asking for.
Huh?
Which compound you are.
Yeah, but what do we need to get quantification?
Molecular.
No, in an instrument, how do I get concentration data? Concentration. What is necessary? Calibration. You need calibration. To do calibration, you need to have, you cannot do calibration for, I can do calibration for general hydrocarbons, but all hydrocarbons may not give me the same calibration chart. So, that is the problem. So, calibration has to be done very specifically for one compound, which means I need to know what the compound is. And very specifically, I need to know if there are different analytes here, A1, A2, A3, A4 and so on. I do not know which peak is what. So, the next part of it is, how do I do calibration? So, the calibration is done. Calibration is a chart between concentration or mass and some response, right. Now, what is the index, what is the quantity of response I am using, what can I use here in the response. So, if I am using a response in this particular, this is a response, right, this is a response, this is the signal I am getting. How can I use this to get a calibration information? Okay. In calibration in gas chromatography, and this I have the chromatogram. Now, let us say I have some peaks like this, and then I need a calibration. This is a chromatogram, and this is a calibration. In the calibration, I will have mass or concentration versus some response. Yeah. So, how do I get the calibration information? I am doing the calibration for a particular type of compound. For I need to do calibration for a particular for some A, for one compound, yeah, for which I need the signal, mass or concentration. So, I have to inject a known amount of of analyte A into the GC, I record the response. Now, how? So, I inject A, so I record the response. This is say M1 or row A2 1. So, let us call it as M1 or we will call it as mass 1 or concentration 1, level 1 concentration. Now, this response here in chromatography, typically the current state is we calculate the area under this peak. So, this signal hopefully corresponds to this particular compound A. As I have injected A, there is one signal that comes. So, corresponding to this one mass, I get one response, and the response here is area. I have one point in my calibration. Then I inject another one. So, I get another chromatogram. So, let us draw this. This is level 1. Then I will draw another chromatogram. The same place I inject another sample, I will get another one. Let us call it as this blue thing. This is level 2. Then I inject the third one. Level 3, then I can inject another fourth one which is smaller than this. So, we will call this as level 1, this is level 2, and this is level 3, this is level 4 for completion. So, this is level 1. Level 2, level 3, level 4. So, we have different areas of this thing. As you can see, the area of level 1 is smaller than 2, 3, 4. So, level 4 is greater than level 3, is greater than level 2, is greater than level 1. So, the area of so, I have 4 points and I can draw a calibration chart through this. So, this is a calibration, which means I need to know what is coming. So, one of the features of the calibration is the information I am getting here is one of the things information I get from a chromatogram. This is on a time axis, right. If I inject compound A with a certain set of conditions with one column and one temperature profile conditions, I can expect that this will come out at one particular time. Compound A will always come out at that particular time as long as you do not change anything. Every time I inject, it should come around the same time. Compound B, which has slightly different properties than A, will come before or after compound A, so on. So, the retention time, the time at which a particular compound comes here is called as a retention time. The retention time is a very important characteristic of an analyte for a given system. So, you have to understand that the retention time will change if I change temperature, if I change the properties of my mobile phase, if I change column. So, if I know this system, if I say I am introducing a sample at retention time 1 at say 2 minutes or 3 minutes, I am always for some peak comes, I know of a certain amount of confidence that it is this particular compound. That is one characteristic of the particular analyte arriving at a particular time. So, it is the retention time, it is characteristic of this. So, if you have compounds that are in a series, so if I have a series, for example, you have a alkanes, series of alkanes with boiling points in the increasing order, I can get series of peaks. this is C3, this is C4, this is C5, C6, C7, C8 for example. And these boiling points are increasing in this order, and the molecular weights are increasing in order. So, you can predict that as this boiling points are increasing, I can see something in this order, peaks will come in this order and so on. This will change if you have functional groups that are added on to this. So, if for example, if you have a compound that has both of them have one has C4 one has and one has one has C5 and one has C3, but this one has say an OH group and this one does not have an OH group. So, this polarity of this this one has an OH group and this one does not have an OH group. The polarity of this may be greater than this. Okay. So, despite being higher molecular boiling point, it may still come out faster because it does not like the mobile stationary phase. It is more polar. If the stationary phase is very non-polar, it does not like, the partition constant is very different of this one. So, in this case what this analyte and this analyte are not similar, and they cannot be, they do not follow a trend simply based on molecular weight or boiling point. It is based on functionality of the functionality of, that is, functional groups attached to it. So, essentially the retention time we know is a function of the partition constant, which now there are three things here, there is A, S and M. The polarity of A with reference to S and M is important. So, if a compound has a polar group, the hydrophobic nature of this compound determines also where the compound will come out, what is its retention in the. So, all these are there points to be considered. So, there is one very important question if you analyze a mixture. So, you have a calibration, that is fine. Okay. I have a chromatogram that is I run a chromatographic analysis of a sample, I get 4 peaks. How do I know which one is what? From? So, to know which one is what, basis for identification is, one is retention time, but we also know that retention time for two compounds can be the same. They can have different boiling points, but if they have a set of functional groups that make their partition constant same, they may both come at the same time. So, retention time alone cannot give you any this thing, but that is the only information we have here. So, one of the things we have to make sure that it is a compound that you are looking at is by injecting standards. So, you inject standard for A1, A2, A3 and A4. You inject A1, only A1, and then you know where it is coming. This is the retention time for A1. Yeah. Then you inject A2, you know the retention time for A2 and so on. You have also verified it because now you have checked it with that particular compound, and therefore, you have a fairly good confidence that A1 is the compound that will come at that retention time. Yeah. But beyond this, you have no identification this thing. So, you have to rely on that alone. Okay. So, it is quite possible that there may be another compound which is exactly behaving the same way as your standard could be. The compound that you are not aware of is there in the sample, that is possible. So, one of the things people do is, the only thing that you can check, verify, cross check this is, if this is really A1 is in your sample, you can spike your sample. So, normally if you have a standard sample, you run a sample, you will get a peak like this, say you get a peak like this. But if you spike your sample, one other thing that may happen is this, if you spike a sample with A, you will see that the next run, if you run the sample again with the spike, you will see an increase in the peak area, which means that it is verification that at the same retention time there is an increase. So, you can have some amount of confidence that it may be this compound, but you still are not sure that it is this compound. You cannot go and tell anybody that this is this compound. So, you can guess, you have to guess, and it is a very complicated game of guessing, because you need to know where your sample is, what is your sample. So, you need to have a lot of information about what is your sample. Okay. Suppose I am collecting exhaust from a automobile, I have a fairly good guess that what my sample will contain. It should contain some products of the combustion that is going on, or it could contain the fuel itself. So, there is not a whole lot of compounds that are there. As against, if I go and collect sample in the middle of the city in the air somewhere, I have no idea what is there, because the air is well mixed, it could be coming from 100 different sources, all kinds of things are there. So, analysis is not very easy, because if I just run an FID program, I will get some peaks, I do not know what is it. It may match with alkanes, it may also match with some benzene or something like that. So, it is very difficult to do this. So, this is a problem with non-selective detectors, but the FID is a very sensitive detector. So, it can go to very low concentrations. It is very widely used in petrochemical industries, because they are interested in separations and all that. So, it is a very commonly used detector. It is a cheap detector, it is not very expensive to get this. So, gas chromatography with an FID is a reasonably inexpensive detector, but it has limitations that it can only analyze hydrocarbons, that is one. The second type of detector that you would have seen is what is called as thermal conductivity detector. Or TCD. This one is also non-selective, which means that it does not give you any specific information about the compound analyte, but this is what is called as a universal detector. It will detect anything. You can detect, you can measure oxygen, hydrogen, carbon dioxide, carbon monoxide, anything that you want. Okay. So, because it is measuring thermal conductivity with a reference. So, if you want to measure thermal conductivity, if you want to measure oxygen content in a sample, you have to, the carrier gas will change. So, there is a reference thermal conductivity of the carrier gas. So, it measures the difference between thermal conductivity of the carrier gas and whatever is there in the carrier gas in the sample. So, if you want to measure amount of helium, you cannot use helium as carrier gas, you have to use something else, which there is some contrast. It could be a negative thermal conductivity difference or a positive. So, the signal in a thermal conductivity detector, the signal can go both ways. This is the baseline, then you can get this kind of signal also, you can get this kind of signal and this kind of signal. So, it is the same thing, it measures the difference between this signal and that one, and the same thing, you have to do calibration in the same manner as we talked about. Everything else is same, except that this can do little more, but it is not as sensitive, because it is a little more universal detector. The sensitivity is not very high, so you cannot go to very low concentrations in the thermal conductivity detector. Yeah. The third kind of detector is called as an electron capture detector. Or an ECD. This is very specific to halogens, this has very high sensitivity to halogens, chlorinated compounds, and very high sensitivity, which means it can go to very low concentrations with chlorinated compounds. So, this was developed because a very large class of compounds, chlorinated compounds, which are of interest to us from an environmental point of view. Okay. So, this becomes very critical that. Okay. But all of these we have the same problem, we really do not know what is the compound. You have to do a lot of pre-processing, in a sense you have to know what is it that we are interested in, and this becomes a problem throughout an analysis, depending on, even if you have more tools at your disposal, you really need to know what is it that you are looking for, which means that you have to have some information about the system, and you can't just go blindly and say I want to know what is everything that is in the sample, which is usually a very bad unreasonable and unachievable target. So, there is a fourth kind of detector that takes the disadvantages of all of this and it can give you a little more information. It is called as a mass spectrometer or a mass selective detector. Okay. So, it is MS, this is called as an MS, mass spectrometer. So, this gives you additional information. What it gives you is, it gives you, in addition to a chromatogram, it gives you another dimension of data. Every time, every bit of sample that is going through undergoes a fragmentation and it gives you a spectrum, it gives you a mass spectrum. And mass spectra are used as a signature of that particular compound to identify. Yeah. So, we will talk about this in the next class, a little bit more about this and how we can use it in environmental analysis. So, this is a, if you go and look at the standard methods a few classes ago, that we look at your methods for GCFID, your methods for GC, ECD, TCD, ECD and for MS, this method for MS, they are all different because sample preparation and the way in which you do calibration is the same, but how you identify compounds, and therefore, you have to be very careful about pre-processing, which means you do a cleanup procedure where you only take one fraction. You take the fraction of, you do a pre-chromatographic separation using a separation, one of those column chromatography methods, and you take only PAHs or only oils, alkanes separating, and then put that into the GC with FID, and the peak will only have that particular fraction. So, then you have a better chance of guessing what the compound is by you have to again be very smart about using the standards, how standards are used to get qualitative as well as quantitative information that you want. Okay, we will stop here tomorrow and we will pick it up.